In the first semester, one of the problems you looked at involving integration was the area between curves. The way you did this back in the first semester was you had the graphs of two functions, f and g, and there were two things that needed to be true for what we're about to write down to be correct. Firstly, both of the functions must only take on values that are positive or zero for x's that lie between a and b. I'm going to need this in order to interpret certain things as areas. And secondly, one of the functions must be above the other one for all x's in AB in terms of the graph. F of x in this particular setup needs to be at least as big as g of x and possibly higher up than that. What we want to do is to calculate the area of the indicated region, and given these two assumptions on f and g, that's not very difficult. Momentarily, let's ignore the presence of the g function and think only of y equal f of x. Based on our previous comments, if I want to know the area that I've shaded in here, this is easy to do. Assuming that f is continuous and positive, this area is just the definite integral from a to b of the f function alone. But that integral doesn't represent the area between the curves because there's no reference to function g in it. I'm going to draw the graph of f again, but I'm going to draw it as a dotted line and think only now about the graph of y equal g of x. Since g is positive and continuous, I can calculate the shaded in area as being the integral from a to b of g of x with respect to x. In the original picture that I've drawn above, the area between the curve needs to have this amount removed from it. That is to say, the cross-hatched area needs to be subtracted away from the first area that we calculated in order to get the area between the curves. So to calculate the area between the curves, I'll integrate the upper function, the f, from a to b, get a number by doing that. I'll integrate the g function from a to b, get a number for that, and then subtract them, writing it as the way people usually do. I'll find the integral from a to b of the upper function, f of x, minus the lower function, g of x, with respect to x. The line of reasoning by which we arrived at this depends crucially on both functions being positive. That's why I can interpret these integrals separately as areas, take one area away from the too big area to achieve the area between the two curves. If I had a horizontal rectangle that was 4 units long, as indicated by the splitting it up into 4 smaller rectangles, if I wanted to know the horizontal length of this, then obviously it's 1 unit, 2, 3, 4 units in length. I want to observe that if I take the number on the number line that goes with the right end and subtract away the number that goes with the left end, I get the length of the horizontal rectangle. The same is true even if I move the rectangle so that the x-coordinates of the left and right end are no longer both positive. if I calculate 3 minus negative 1, I still get 4, which is the length of the horizontal rectangle. If both coordinates are negative, it makes no difference. The rightmost value is the biggest one, and the leftmost value is the smallest one. If you calculate biggest minus smallest, you end up with 4 again. So if I have a horizontal number line, which I could probably just go on and start thinking of as the x-axis, and I have some object adjacent to it, next to it, and I want to know how long the object is, regardless if the coordinates are positive, negative, 0, it doesn't make any difference. Take the biggest one, the rightmost one, minus the smallest one, the leftmost one. Biggest minus smallest will always give you the length of the horizontal rectangle. Now, all of these thoughts have involved a number line and a thin rectangular strip of material laid out parallel to it. I've drawn my number line horizontal, thinking in my head secretly of it being the x-axis, but that doesn't need to be the case. I could tilt these number lines, and all of the calculations would work out the same. I could tilt them so much that what used to be horizontal is now vertical. Instead of having the biggest x number minus the smallest x number, that is to say the x number that is the most to the right minus the one that's most to the left, I'll have the biggest y number minus the smallest y number, or the y that's as up as possible minus the y that's as down as possible. All of the calculations will work exactly the same way. Going back to the shapes that we're interested in, I'm going to imagine starting at x equal a and ending at x equal b. I'll have something up at the top, the graph of y equal f of x, something at the bottom, y equal g of x. Notice I haven't indicated whether this picture that I've drawn is completely above the x-axis, partly below it, or totally below it. Because I don't care, it doesn't make any difference. What we're going to do is the following procedure. We're going to set up a partition of the interval of x numbers from x0 equal a to xn equal b. I've drawn my number line below the region. This is just for purposes of reference. I don't care if the region is above or below this horizontal line. This divides my region, whose area that I want to know, up into a bunch of smaller chunks, each one of which almost looks like a rectangle. Let's think about one of these in particular. I'm going to think of looking at chunk number j. The horizontal chunk ends at x number j and begins at x number j minus 1. The horizontal width of it is delta x number j. There will be one of these roughly rectangular shapes to go with it. For instance, it might be this one. Within subinterval number j, pick some particular value of the independent variable, which is x in this case. Call that value c number j. In the small chunk that I'm looking at, there are x coordinates within the chunk that have value Cj, and a variety of y coordinates that go with them. Between the graph of g of x and this part of what I'm calling the x-axis, there are no points of my region of interest. Above this point, there are no points in the region of interest. I'm going to approximate this region by a rectangle that's delta x number j horizontally. To find its area, all I have to do is to estimate the height of it. Using my representative x value for subchunk number j, the top will be characterized by having y coordinate f of cj, while the lower part will have y coordinate y equal g of cj. To get the height, I do the upper minus the lower, just as we did on the number line. The way I calculate the area of a rectangle is I take the positive base length and multiply it by the positive vertical height. So the area of that one chunk is approximately given by the vertical height, f of cj minus g of cj, multiplied by delta x number j. This is an approximation for the area between the two curves that corresponds to chunk number j. To approximate the area between the two curves all the way from x equal a to x equal b, I'll just add up all of the estimates of areas of these nearly rectangular regions and get the sum, j equal 1 to n, f of cj minus g of cj times delta x number j. This is only an approximation though, but as I make all of the delta x's smaller, we expect the approximations to become better. So we will take the limit as the norm of the partition tends to 0. That is to say, as all of the delta xj's tend to 0, and we recognize this as the definition of something. I have the limit of a sum. The name of the independent variable is x, and I have delta x number j as a factor. I have some expression or quantity that involves c number j. According to our recipe, the limit of some symbol turns into an integral sign. The delta xj's turn into dx. In what remains, I stop writing down the letter that represents the typical independent variable value on chunk number j, and just start writing down the name of the independent variable instead, and then finish the formulation by having the lower limits of integration being a and b. So all I require now is that the f be above the g. I don't care if f is positive or negative, or if g is positive or negative. As long as f is above g, the area between the two curves is the integral from a to b of f of x minus g of x with respect to x. Naturally, this is the same formula we got back from Calc 1, but this formula is better because it works even when the f and the g are not always positive. We got this by splitting the problem up into little rectangles, thinking about the areas of the rectangles, adding them all up, and allowing them to become indefinitely thin in the horizontal direction. The reason that we're going through all this stuff is not that we get a new and improved formula for calculating the area between curves. Although in a certain sense we have, the idea is to start thinking about integration as taking limits of sums, because that's our trick for Chapter 7. As an example of this, I want to think about the area between the graph of y equal x and y equal negative x squared, starting at x equal 1 and ending at x equal 3. Now, of course, we already know what's going to happen. We could just write the integral down, but that's not the point to what we're doing here. The point is to split the range of values that the x, the independent variable, can take on up into a large collection of smaller chunks, the subintervals that we've been speaking of. We divide the x range, in this case, from 1 to 3 up into a large number of smaller subchunks, and then we're going to think about one of these subchunks. Blowing the picture up a little bit and separating the chunks, I'm going to think about chunk number j. In terms of the independent variable, chunk j begins at xj minus 1, ends at xj, and we're going to pick some representative c value, cj, as a particular x number from this one chunk. The function above is f of x equals x. The function below is g of x equals negative of x squared. Evaluating the upper and lower functions at c number I get above that y is just c number j, that is, and below y is the negative of c number j squared. To get the vertical height, I take the upper and subtract the lower. To get an approximation for the area that goes with chunk number I need to multiply by the horizontal width of chunk number I mean, of course, chunk number j. Having these estimates, I need to add them all up. This gives me an estimate for the total area between the two graphs. To make the estimate perfect, I'll have to allow all of the widths of subchunks to tend to 0. And once again, following our recipe, limit of sum is going to turn into an integral sign. Delta x with the index, in this case j, turns into dx. What's left is an expression that involves c number j. I'm just going to stop writing c number j down and start writing the name of the independent variable instead. To complete the setup of the integral, I have to put in the smallest and largest relevant independent variable values, largest and smallest x values in this case. That would be x equal 1 and x equal 3. As I said before, based on what we know already, we could have just written this integral down, but that's not the point. The point is to think of chopping the region up into easy to deal with pieces, thinking about one of the pieces, that one in this case, figuring upper minus lower times width, and then take the limit to turn it into an integral. And then, of course, we have ways of calculating the integral. Actually, doing the integral is easy. Write x minus the negative of x squared is x plus x squared, so it doesn't look so bad. Find an antiderivative, x squared over 2 plus x cubed over 3. Evaluate at x equals 3 and at x equals 1, then subtract, and get 12 and 2/3 for an answer. Sometimes problems are stated in other ways. This sometimes causes people a lot of mental confusion, so I want to look at one of those too. Rather than having y as a function of x, I'd like to have x as a function of y. One of my two graphs will be x equals sine of y, where the y can go from y equals 0 to y equal pi. The other graph is going to be the vertical line where all of the x coordinates are equal to 1/2. And what I want to calculate is the area that's to the right of the vertical line, but to the left of the first graph. I want to calculate the area of this region. If I didn't know any better, my first thought would be to solve for y in terms of x and then just do the same thing that we've been doing. That's going to turn into a problem where I have to integrate the inverse sine function, and officially we don't know how to do that yet. Instead, I think I'm just going to deal with it as is. As is, instead of having vertical rectangles like we did before, I'm going to have horizontal rectangles. Instead of chopping the x range up into a bunch of smaller values, I'll do it for the y range instead. I'll have a little side issue. I'm going to have to figure out what the smallest y value in my region is, and also the largest y value. That'll just be a little bit of trigonometry for now. So for the moment, I'm going to presume that I've done that. If I divide the range of relevant y values up into a collection of smaller intervals, since this line is parallel to the y-axis, it gets divided up in that way as well. I'm going to think about the relevant points that go with one of these sub-intervals. I'll have a horizontal rectangle. The vertical extent of it I'll call delta y number j, since y is the independent variable value now. My rectangle is horizontal. The other dimension of it is the biggest x value minus the smallest x value. The biggest x value is the x value on x equals sine of y that goes with my representative y value this time. So the horizontal length of that one particular rectangle is sine of Cj minus 1/2. This will be true for all the different subchunks that we're looking at. The area of that one particular rectangle is approximately what I get when I multiply delta y number j by sine of Cj minus 1/2 to get an estimate for the total area. We can just add up all these estimates. To make the estimates perfect, we'll have to take the limit as all of the size of subchunks goes to 0. We'll take the limit as delta norm tends to 0, where this time around, for a given partition, the norm of delta is the biggest of the delta y numbers, not delta x numbers. It's important to grasp this thought. There is no x in this problem. The independent variable is y. I have a delta y down at the end. The Cj is not an x number, but a y number instead. So when I turn this into an integral, limit of sum turns into an integral sign again. The delta y's turn into dy now, and the cj's turn into not x but y instead. We have to put in the biggest and smallest y values, and then we can do our integral. Hopefully the fact that the variable of integration is something other than x is not too disturbing by this stage of the game. My original graphs were x equals sine of y and x equals 1/2. If I'm to find these 2 points of intersection, I'm looking for y values so that sine of y will equal to 1/2. Also, I'm only interested in y values that are between 0 and pi. One solution is easy to get. One solution of sine of theta equals 1/2 is theta equals arc sine, or inverse sine, of 1/2, which is pi over 6 radians. I need another angle in the range from 0 to pi, 0 to 180 degrees, that will also give me sine of theta equals 1/2. On the unit circle, the sine of an angle is the y-coordinate of the point on the unit circle. So I'm looking for another point in quadrant 1 or quadrant 2 on the unit circle that has y-coordinate equal to 1/2. Because of the symmetry, that angle is short of being a full pi radians by pi over 6 radians. Therefore, that angle must be 5 pi over 6 radians. There are two values in the range 0 to pi which will make sine of the angle equal to 1/2. One of them is pi over 6, the other is 5 pi over 6. These are the limits of integration on our integral. Dealing with the fact that there's no x in this problem at all, only y, this is now an easy integral to calculate. The antiderivative is negative cosine y minus 1/2 y. I must evaluate that at y equals 5 pi over 6, also at y equal pi over 6, and then subtract. Evaluating this is straightforward. The exact answer is square root of 3 minus pi over 3. In decimal to 5 significant figures, that's 0.68485. Situations can be slightly more complicated, though. If a person were asked to calculate the area between y equal x and y equal negative x, for x's that were between -1 and +1, if they didn't know any better, they would think to themselves, the smaller one is the one with the negative sign on it. They would say integral -1 to +1 of x minus the negative of x with respect to x. The integral from -1 to 1 of 2x with respect to x, which has an antiderivative of x squared. If you evaluate x squared at either 1 or -1, though, you get 1 for answer. Subtracting, you get 0. This is obviously wrong. There's going to be some region in the plane. It's going to have some area. Areas of regions that actually have anything to them are not 0. The problem is obvious. The region is going to be determined by what the graphs of y equal x and y equal negative x look like between -1 and +1. If I draw both graphs on the same graph, if x is positive, if it's to the right of the y-axis, then obviously the upper y value is y equal x, and the lower one is y equal -x. This is not the case if x is negative, though. If x is negative, the upper one is y equal -x, and the lower one is y equal x. So if I wanted to do this, thinking of it as being made up of these rectangles, I really should split this up into two chunks. I should look at the part from -1 to 0 separately. The upper is -x, the lower is x. I should do that part separately, and then deal with the rest of it, where x is the part that's above and -x is the part that's below. We've seen problems like this in the first semester, but I thought it was worthwhile to at least mention this. As I said at the beginning, we already knew what the answer was going to be, but we have a new way of thinking. We're thinking about this in terms of an accumulation process. We are adding up or accumulating the contributions that come from each one of these little rectangles. We add them up to get an estimate. We take a limit to make it exact, and then we use our bag of tricks for integrals to figure out what the limit is equal to. In the next discussion, we'll start looking at some problems that we don't already know the answer to. Until then, I hope everyone's having a good day, and I'll talk to you again soon.